Welcome to the course, A Foundation for Machine Learning and Data Science, section Python and Overview, Python Data Types and Structures, NumPy Data Structures. In the first subsection of Python Overview section, we will be reviewing the following: Python's native data types and data structures, NumPy data structures, and Python operators. I'll be showing lots of code snippets throughout this Python Overview section just to give you an idea of how to implement the concepts discussed. If you cannot understand the code snippets completely, no worries. I'll be executing all these code snippets in the hands-on sections. What is Python? Python is an interpreted high-level general-purpose language preferred by data science and machine learning practitioners. It's an interpreter where the source code is executed line by line, unlike compilers. It's easy to learn and the language of choice for machine learning and data science programmers. It's a fully featured language, which means it has a full capabilities for data acquisition, exploratory data analysis, data pre-processing, data modeling, high performance, and much more. It has a strong data science and machine learning libraries such as NumPy, Pandas, sklearn, Matplotlib, Seaborn, Plotly, etc. In general, what are the data types and data structures available in Python? Python's native data types, Python's native data structures, NumPy's data structures, and Pandas data structures. Integer, float, string, and boolean are the data types available in Python. Tuple, list, dictionary, and set are the data structures available in Python. The array is the primary data structure available in NumPy, and series, data frame, and index are the data structures available in Pandas. Apart from these, there could be other data types and data structures as well, but they are outside the scope of this course and we will not be discussing them. There are 4 data types in Python, and they are integer, float, string, and boolean. Integers represented as int are whole numbers without a decimal point, example the number 5. Floating point numbers represented as a float are real numbers with a decimal point, example the number 5.2. Strings, a sequence of characters enclosed within single quotes or double quotes, example Balasubramanian Chandran. Boolean value, represented as bool that will have only true or false value. There are 4 data structures in Python, and they are tuples, lists, dictionaries, and sets. Tuples are immutable and cannot be changed once created. They are created using parentheses, example 1a, 2b. Items do have ordering, which means the items can be accessed through indices and iterable by items only. Lists are mutable and can be changed after creation. They are created using square brackets, example 1a, 2b, and 5.2, surrounded by square brackets. Items do have ordering, which means the items can be accessed through indices and iterable by items only, just like tuples. Dictionaries are similar to tuples and lists, but items do not have an ordering, which means every item has an explicit index defined. They are created using curly brackets. Example, item 1, 1, item 2a, item 3, 2, item 4, b. Here, item 1, item 2, item 3, and item 4 are indices. The actual dictionary values are 1, a, 2, and b. Dictionaries are iterable by items or by values or by both together. Set. A set is a collection of unique data. The elements can be of mixed data types but cannot be duplicates. Sets are created using curly brackets, similar to dictionaries but without indices. An example, ML101, number 5, number -10, thank you, surrounded by curly brackets. Items do not have an ordering and do not have indices. Sets are iterable using for loops. NumPy data structures, arrays. The array is the primary data structure in NumPy that can hold multiple values of the same data type. Arrays can have multiple dimensions such as 1D array, 2D array, 3D array, etc. Arrays can be manipulated in 5 different ways, that is, using their attributes, using their indices, using slicing mechanism, using reshaping mechanism, and by splitting and concatenation. We can use array attributes to find out the size, shape, memory consumption, and data types of arrays. We can use array indexing to access and set the value of individual array elements. We can use array slicing to access and set smaller subarrays within a larger array. We can use array reshaping to transform the shape of an array. We can use array splitting and concatenation to split one array into many and combine multiple arrays into one. Array computations using universal functions called ufuncs. The computations of the NumPy array can be very fast or very slow. The key to making it fast is to use vectorized operations, where the operations are performed in compiled code. Ufuncs are NumPy functions that operate on 1D and multidimensional ND arrays. Ufuncs implement vectorization, no looping over array elements, which is way faster than iterating over elements. Ufuncs support broadcasting, a set of rules for applying arithmetic operations on arrays of different shapes, and typecasting, converting one data type to another. Examples of ufuncs in NumPy: addition, subtraction, multiplication, division, float division, negation, exponentiation, modulus or remainder, and absolute value. What is vectorization? A technique of performing mathematical operations on elements of entire arrays, eliminating the need to loop through individual elements. Simply, it is converting iterative statements into vector-based operations. Code runs fast and it is easy to read. It's always recommended to use NumPy's ufuncs to perform arithmetic operations on arrays instead of using loops for performance gains. Array aggregations using ufuncs. Ufuncs can be used for aggregate functions such as min, max, sum, etc. on 1D and multidimensional arrays. Whenever possible, use the NumPy version of the aggregate ufuncs while operating on NumPy arrays for performance gain. Aggregate functions using ufuncs: sum of elements, product of elements, minimum value of elements, maximum value of elements, index of minimum value, index of maximum value, mean of elements, median of elements, percentile of an element, standard deviation of elements, variance of elements, evaluate if any elements are true, evaluate if all elements are true. Array broadcasting. Another way of vectorizing operations is to use NumPy's broadcasting functionality without using ufuncs. Broadcasting is a set of rules for applying binary ufuncs such as addition, subtraction, multiplication, etc. on arrays of different sizes. Rules to determine the interaction between two arrays. Rule number 1. If the two arrays differ in their number of dimensions, the shape of the one with fewer dimension is padded with ones on the left side. Rule number 2. If the shapes of the two arrays do not match in any dimension, the array with shape equal to 1 in that dimension is stretched to match the other shape. Rule number 3. If in any dimension the sizes disagree and neither is equal to 1, an error is raised. Let me explain the broadcasting rules with a couple of examples. Adding a scalar to a one-dimensional array to demonstrate rule number 1. First, let's create a 1D array with the dimension 1 by 3 and add a scalar 6 to it. The Python code to do it is as shown. This is the 1D array and we want to add a scalar to this array. Here, the scalar is padded with the 2 more 6s to match the dimension of the 1D array on the left side. This operation will give us the result as shown here. Adding a 1D array with a 2D array to demonstrate rule number 2. First, let's create a 2D array with the dimensions 3 by 3 and add 1D array with the dimension 1 by 3. The Python code to do it is as shown. This is the 2D array and we want to add this 1D array to the 2D array. Here, the 1D array is padded with the 2 more rows to match the dimension of the 2D array on the left side. This operation will get us the result as shown. Adding two one-dimensional arrays with 2 different dimensions to demonstrate rule number 2, that is, broadcasting both arrays. First, let's create a one-dimensional array with the dimensions 3 by 1 and add another one-dimensional array with the dimensions 1 by 3. The Python code to do it is as shown. This is the one-dimensional array and we want to add this one-dimensional array to the first one-dimensional array. Here, both the one-dimensional arrays are padded with 2 more rows and columns respectively as shown to make them 2-dimensional arrays with the dimensions 3 by 3. This operation will get us the result as shown here. Boolean masking, a feature in NumPy that filters values from a given array, produces a subarray containing only truth values, true or false, that correspond to each element in the given array based on some criterion. Boolean masking is used to examine and manipulate the values in arrays such as extract, count, modify, etc. Boolean masking enables faster execution. Examples: count all values greater than a certain value in an array, identify and remove all the outliers that are above some threshold. Consider an array A whose values are 1, 2, 3, 4, and 5. Try to find out the value less than 3 in the array. The Boolean masking creates an Boolean array true, true, false, false, and false because the first 2 elements 1 and 2 are less than 3, hence true and true. 3, the third element, is equal to 3, not less than, hence false. Then the elements 4 and 5 are greater than 3 and hence false and false. Comparison operators for Boolean masking: equal to, not equal to, less than or equal to, greater than or equal to. When you use arithmetic operators, addition, subtraction, multiplication, division, etc., and comparison operators, equal to, not equal to, less than or equal to, greater than or equal to, etc. on NumPy arrays, they are implemented as ufuncs in NumPy internally. Fancy indexing: passing an array of indices in place of a single scalar to access multiple array elements at once. It helps to quickly access and modify complicated subsets of an array's values. It works in one-dimensional and multi-dimensional arrays. Example 1. Accessing array elements using fancy indexing like this. Example 2. Combining fancy indexing with the simple indices like this. Example 3. Combining fancy indexing with slicing like this. Example 4. Modifying values of an array using fancy indexing like this. While using fancy indexing, the shape of the result reflects the shape of the index arrays rather than the shape of the array being indexed. Sorting 1D arrays. Use NumPy's npsort and nparcsort functions to sort arrays instead of using Python's built-in sort or sorted functions for performance gain. Example 1. Sort an array without changing the values in the input array. Here, the output array is sorted, but the input array A remains the same. Example 2. Sort an array in place. Here, both the output array and the input array are sorted ones. Example 3. Argsort function returns the indices of the sorted elements of an array. Remember, in Python, the array elements are zero indexed, meaning the index value of the first element is 0, the second element is 1, the third element is 2, and so on. And hence, the index values of the sorted array elements are 4, 1, 0, 2, and 3. If needed, the index can be used in fancy indexing as well. Sorting multi-dimensional arrays along rows and columns using axis parameter. Axis equal to 0 sorts each column of A. Axis equal to 1 sorts each row of A. When you are dealing with the 2D arrays, use axis equal to 0 for column-wise operations, that is, operations across all rows for each column. Use axis equal to 1 for row-wise operations, that is, operations across all columns for each row. Structured arrays. Usually, the data are represented by homogeneous array of values, that is, an array of integers or an array of floats or an array of strings, etc. Structured arrays represent arrays with compound data types and heterogeneous data. Structured arrays for compound data types. Homogeneous data types are simple arrays and there are no relationships between the data items. Here are some examples. These names are not related. Likewise, these ages are not related. The salaries are not related. Heterogeneous data types are structured arrays with relationships. For example, the employee name, age, and salary, all three are related to a particular employee. Access values either by index or by name. Here are some examples to access names by index and using Boolean masking. The shortened string format codes. Small b for byte, small I for signed integer, small u for unsigned integer, small f for floating point, small c for complex floating point, capital S and small a for string, capital U for Unicode string, capital V for raw data. While the structured arrays shown here are useful for simple operations, the better alternative is to use data frames for such and much more complex scenarios. These are the NumPy's standard data types. You may pause the video and have a closer look into this if you would like. What are the available Python operators? Python operators are divided into 7 categories, and they are arithmetic operators, assignment operators, comparison operators, logical operators, identity operators, membership operators, and bitwise operators. Arithmetic operators are used to perform mathematical operations. Assignment operators are used to assign values to variables. Comparison operators are used to compare two values. Logical operators are used to combine conditional statements. Identity operators are used to compare objects if they are actually the same objects. Membership operators are used to test if a sequence is present in an object. Bitwise operators are used to compare binary numbers. Let's take a closer look at the Python operators. Python arithmetic operators, Python assignment operators, Python comparison operators, Python logical operators, Python identity operators, Python membership operators, and Python bitwise operators. You may pause the video and have a closer look at these tables. With all these operators, it's very important to understand the operator precedence. Operator precedence describes the order in which operations are performed. If two operators have the same precedence, the expression is evaluated from left to right. Examples: parenthesis has the highest precedence, that is, the expressions inside parenthesis will be evaluated first, as given in the first example. Multiplication has the higher precedence than addition, therefore, multiplications are evaluated before additions, as given in the second example. Here is a table depicting the operator precedence. I would suggest that you pause the video and have a closer look at this table. With this, I'll conclude this video and I will see you in my next video, Python Overview Hands-on 1. If you have not done so yet, please rate and comment on this course as it will mean a lot to me.